That leads us directly then into what we consider the ultimate of our effort in General Electric Company, namely applying all of this new modeling concept to a new challenge which was put to us by one of our customer companies. They had an idea for a radar which required a tube that would be able to have a very high data rate in the form of pulse trains put through it. The tubes that we've described so far are what are called diode-type guns, namely the high voltage is turned on or off by a very large pulse modulator, which of necessity has a modest response time capability, namely a rise time of 1/10 or 2/10 of a microsecond. This project required a very high data rate, and in order to do that, we had to come up with an electron beam that was obtained by a DC potential applied to the electron gun, and an intermediate electrode, a grid, that could have applied to it a controlling voltage to modulate that beam on and off at a very high rate, known as a control gridded gun. We were given this challenge roughly 1969-1960 to develop not only that gridded gun, but a broadband design. This again at 3 gigahertz range of frequencies, over 10% bandwidth, and in a tube that had to have a particular size and shape limit because this was going to be a radar flying in an airplane, and has since been labeled the AWACS radar, Airborne Warning and Control Radar, which has been used very widely throughout the world. It has a capability of very high target resolution and also the ability to look straight down from an aircraft to detect motion on the ground without the ground reflection masking everything. Well, I have here one of those tubes, and it represents the last production tube that General Electric made before exiting the business. Again, it has the electron beam formation gun at the bottom, which in this case, as I said, has a very elaborate grid structure. The operating voltage is over 100,000 volts DC, and the requirement was that there should be no sparking or arcing more than one every 48 hours. And we were able to meet that, but only by dint of a lot of careful technology, because a experience that had been obtained over many years with high voltage tubes for ordinary broadcasting and TV and FM enabled people to learn how to polish parts, clean parts, and develop a very good vacuum.
I think you ought to mention at this point that Bob Watson spent a good deal of time and effort into developing these techniques.
He's the engineer. If any one person is in charge of the technology administration, if you will, he's the one. There were a number of people who helped him, of course, but he was the one who was calling the shots, as it were. So here we have the electron gun. We have a number of resonant cavities. These are smaller now. In this case, the frequency is higher. They're these little cans. The RF driving power for this amplifier comes in a coaxial transmission line here. The broad banding of the interaction is obtained in part by some power loads which are applied to the intermediate cavities, which are these appendages here, and they have to be water cooled because of the average power dissipation. And finally ending up in, again, an output cavity, and instead of coming out in this large waveguide horn that we saw in the first tube, it comes out at right angles in a smaller waveguide because of the higher frequency. This is about 1/3 the wavelength of the other one, or 3 times the frequency. And this is the output connection here that would go to the antenna. The collector is a very large box here, again, water cooled. And power output of 1 megawatt of peak power. Average power is, again, in this case, in the order of 5 kilowatts. This tube was made in large quantity, applied to all of the radar systems. General Electric remained the sole supplier of that tube until it decided to quit the business in the end of the 1970s. So this represents the combination of a lot of technology know-how and design know-how, largely obtained by means of modeling, and is about where the state of the art in klystrons is as of 1990.